Consider the problem f of xy equals xy. G of xy equals x squared plus y squared minus 4. Now, I've used this curve in a couple of videos. It's just a circle radius 2 about the origin. So it's very straightforward. And the constraint curve might be more complicated, but this is quite a decent representation of what a constraint curve means and how we might graph the thing. Okay, what we want to do is we want to find points at which f of xy takes its maximum and minimum values as we move around the constraint curve. So what's the situation? Well, let's just review that again a little bit. The rate of change of xy along g of xy equals 0. That is the rate of change of the f function as you move along the g of xy equals 0 curve, the level curve of the g of xy function. That rate of change is 0 if the tangent to g of xy equals 0 is perpendicular to the gradient of f, because the tangent is the direction in which you're moving at a given point of the g equals 0 curve. If the gradient of f is perpendicular to that tangent, that means gradient of f being the direction and constituting the direction and magnitude of the maximum increase. So the direction of del f being the direction of maximum increase, that vector has no component in the direction of the tangent vector, meaning that the rate of change of f in the direction of the tangent vector is 0, because perpendicular to your direction of maximum increase, you have the direction of no change. Okay, so that's perpendicular to del f, and the tangent to g of xy is also perpendicular to the gradient of g, a property of any level curve. Okay, the gradient of a level curve is always perpendicular to that. The gradient of the function for which you're considering the level curve is always perpendicular to the gradient of that function. So, two important concepts. It follows then that the rate of change of f of x naught y naught along the curve g of xy is 0 if the gradient is parallel to del g. Because why? The tangent has to be perpendicular to del f, and the tangent is perpendicular to del g. Okay, so del f isn't going to be perpendicular to the level curve unless it's parallel to del g, meaning that del f is a multiple, a constant multiple of del g. So that at the point x naught y naught, where you're considering the possibility of a maximum or minimum, del f has to be parallel to del g. Del f has to be a multiple of del g, constant multiple of del g, and we let lambda be the constant multiple. Okay, so, and reading this just a little more in detail, the tangent has to be perpendicular to del f. The rate of change of g in the direction tangent of the tangent is 0, so that the tangent has to be perpendicular to del g. Del g giving you the direction of maximum rate of change of g. Okay, and so forth. Okay, well, let's apply it. Okay, so just looking at where I went first. Okay, I do del f and del g here. I was thinking maybe I'd start it over here. Del f and del g are easily calculated, and I'm not going to go over the calculation. It's very straightforward. So that del f equals lambda del g gives you what? It gives you, well, this component of del f is lambda times this component of del f. So you have what? Skipping a step here, you're going to have this component equal to lambda times this, which means that this minus lambda times this is going to equal 0. So I happen to write it in this form. Okay, and then the condition that this be lambda times this is written equally easily in this form. And now we can solve for x, and x from this equation is just going to be y over 2 lambda, and y is going to be x over 2 lambda. Okay, this is possible, but if and only if lambda equals plus or minus 1 is easily worked out. So that we have y equals x or y equals negative x. Okay, now I'm not going to go through all the algebra of how you analyze this, but you end up, if lambda is anything except 1, then, well, I'd have to write it out. I don't want to explain it. Let's just accept this. Okay. Over here, what's our picture look like? Okay. Now again, this tells you that either y equals x or y has to equal negative x. If you're on the curve, either y equals x along this line, y equals negative x along this line. These lines both being lines of slope 1 or negative 1. Slope 1 here, slope negative 1 here. So you're talking about halfway between here and here on the curve, halfway between here and here on the curve, and so forth. Why does this work out? Let's look at del G and del F. Okay, del G is always the direction perpendicular to the curve. So del G is the purple vector, here, 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 or here. And del F is the vector yi plus xj. Now if you do yi plus xj at this point, x is 2, y is 0, so you have no I, 2j. So the del F vector, which I probably should go ahead and label, is going to be this. Now, if y equals x, as it does here, then the del F vector will have equal I and j components. It'll be straight away from the origin, a radial vector. So del F will be like this. Now if you get out to the point where x equals 0 and y equals 2, you have 2i and no j. Well, that's going to give you a del F in this direction. And these vectors, as it turns out, this vector will have magnitude 2, this vector will have magnitude square root of 2, so the lengths of these vectors aren't representative. I just sketched vectors in the appropriate direction. So anyhow, this is the direction of your del F. You can correct for the magnitudes, and just basically need to make this one a lot shorter. And as we move around, you see how the del F and del G vectors line up. Here, they're perpendicular. So that if you move in this direction along the curve, you're moving at this point in the direction of maximum increase of your f function. Your f function is going to be changing here. You're not going to have a max or a min here. It's going to go from a lower value to a higher value, and there's not going to be a max or min at this point on the curve. Okay, if you're here, del F is parallel to del G. It's perpendicular to the direction of G, so if you're moving in the direction of the curve at this point, you have no rate of change of f. So that this point is a candidate for relative max or relative min. Okay, move to this point, again, your del F is in the direction exactly opposite your motion if you happen to be moving counterclockwise, and your G function, I'm sorry, your f function, while you're on this curve, is going to be decreasing at a maximal rate. Okay, now you get over here, and again, del F is in the same direction as del G. Your y is negative, your x is positive, so you get this alignment between del F and del G, motion along the curve is in this direction perpendicular to del G, so that there's no component of your del F in the direction of motion. So again, you have a possibility of a maximum or a minimum. And the same goes for all the rest of the points that I've sketched on the circle. So you have relative maxima or relative minima at this point, at this point, at this point, and this point. Each of these points is a candidate for relative maximum or minimum. We're not guaranteed, in fact, that you have a relative max or min at any of these points. But if there are relative maxes or mins, they have to occur at these 4 points. Okay, so if we evaluate the function at these points, we easily find that this point, where the magnitude of the function is square root of 2 squared plus square root of 2 squared, the magnitude of the f function is the product of the two components, and I think I said before that sometimes the magnitude is greater and sometimes the magnitude is less. At this point, the x-coordinate is square root of 2, y-coordinate is square root of 2, square those and add them up, you get 2 plus 2, 4, the magnitude is 2, just as it was here. Okay, so actually this del F vector and this del F vector should have the same magnitude, and I kind of misspoke on that earlier. That's not particularly relevant to the question, but I wanted to correct that little error. Okay, so at this point, x is square root of 2, y is square root of 2, xy is equal to what? 2. So your value of the function here is 2. What about this point? Well, x and y both have magnitude square root of 2, but in this case they have opposite signs, so that the magnitude of f is negative 2. And then at this point the magnitude of f is 2, and at this point the magnitude of f is negative 2. So we see that we have a maximum value here, a minimum value here, a maximum value here, a minimum value here. On the coordinate axes, either x, at any point on either coordinate axis, either x or y is going to be 0, so the function is going to be 0. So we could say that f is 0 here, f is 0 here, f is 0 here, and f is 0 here. So we go from 0 to 2 to 0 to negative 2 to 0 to 2 to 0 to negative 2 and back to 0. Interesting question. Does the value of the function increase linearly up to this and then decrease? Well, you wouldn't expect that, because you wouldn't expect the value function to have a sharp point, as it would be if you had a linear up to here and then a linear back down to here. You might think about that. We could easily enough sketch the values of x, y, and compare this to the quadratic surface that you get for f of x, y equals x, y. It's going to be hyperboloid, and you can consider what you know about the graph of that hyperboloid. You could consider the second derivative test for max and min. You could consider a lot of things about the hyperboloid to understand the graph of that hyperboloid, and then see how that graph articulates or intersects the constraint x squared plus y squared minus 4. Again, you have the graph of the function out here in three-dimensional space, and the cylinder x squared plus y squared minus 4 equals 0, which is just x squared plus y squared equals 2. How does that cylinder intersect that hyperboloid?